coordinates version of fluid flow. Specifically, these are the Euler equations in polar coordinates for an incompressible fluid. So here's the big question. What happens if we want a smooth... If we want a smooth and incompressible flow, which means density is a constant, which is also radially symmetric, what conditions need to take place? Well, axisymmetricity implies that any of these guys go to 0. So this all simplifies to, well, this disappears, and keep in mind the u and v are just the components of the velocity vector. And this guy disappears too. Oh, and so does this guy because it's a derivative with respect to theta. Okay, so this all reduces to rho ut plus u partial derivative of u with respect to r minus v squared over r, which is equal to over r. Meanwhile, here we can eliminate the density constant and just get Vt plus u multiplied by the partial derivative of v with respect to r minus uv over r is equal to 0. Finally, you get 1 over r, and you can actually expand that part. This becomes, by the product rule, r partial u partial r plus u, because partial r is 1. So that gives you ur plus u over r is 0. Now this is the most important part because it allows us to solve for some function of u. Well, technically, we still don't know because this only involves r and not t. So by separation of variables, you can write it like this since we're not concerned with the part that's dependent on t. So you get du is equal to minus 1 over u du is equal to 1 over r dr. And so minus ln of u plus c is equal to ln r. Now remember that minus ln u is equivalent to ln 1 over u. So that gives you 1 over u times e to the c is equal to, and remember, this is not just c, it's c of t. Because you're integrating u, which is a function of both r and t, not just r. So this could be a function of t, and it would disappear when you took the derivative with respect to r, hence we have to add it back in. Hence, taking the reciprocal, this is essentially u is equal to 1 over r multiplied by some function of t, f of t. However, you have to realize that we want something smooth. And you'll also realize that f of t over r is not going to be smooth at r equals 0. Unless, of course...
People said no sound. What happened? I did not give you the mic.
You did. Okay. F of t is equal to 0.
Sound is not there. 1 second. Let me check the computer. 1 second.
Okay, so that means the radial component is totally missing. We only have a tangential component. And so, what does that mean here? Well, that allows us to disappear everything with a u inside. So this is gone. Just gives us 0 equals 0. Not very useful. And this goes away. This goes away. You just get this. This goes away. This goes away.
Hopefully that when I solve the problem, baby.
You just get this. And now you'll notice Vt is equal to 0, which means V is only a function of R. This is a steady state problem. Vt is equal to 0, which steady state.
I think the sound is okay now.
Okay, so Bernoulli's equation says that the pressure divided by the density plus the velocity squared over 2, and yes, this is the magnitude of the velocity, but V is, the magnitude of V is the exact same as the magnitude of U at this point. So this is constant, which means if you take the derivative with respect to R, well, it's ddr at this point because everything's just a function of R. Well, this becomes 0, and this becomes PR rho plus 2V VR over 2. These cancel each other out, and you get this. So we also have from up here, PV squared over R is equal to PR, rho V squared over R is equal to PR, or V squared over R is equal to PR over rho, which gives this. And so dividing down by V, this. Hence VR is equal to minus V over R, which means that V is equal to what? Well, you use separation of variables again. Multiply this side by dr. And this is largely the exact same thing that we got last time. It just V is equal to C over R. So V is equal to C over R. What does that mean? Well, rho of PR over rho is equal to this squared over R again. So this is just C squared over R cubed. So now all we have to do is integrate it since this is a single variable function. Now, integrating on both sides with respect to R gives us what? Well, the integral of 1 over R cubed dr, you just use the reverse power rule and obtain 1 over R squared multiplied by negative 2. So in this case, you get minus 2C squared rho over R squared plus some extra constant C1, which means that the pressure and the velocity have to follow some very strict conditions. In fact, VR is not just only dependent on R. V is equal to C over R. That's the exact relation that we've established. And so that means P has to be rho over R squared plus C1. So these are the conditions when you unite only these three conditions, which seem incredibly general. It boils down to something very specific. So that's it. Thank you everybody for watching, and we'll see you in the next one.